All right, another video. This one's on hybridization. This is going to be a short one. So first of all, um, we have to go back to valence bond theory. And this just says that there's a natural attraction between all molecules. So if we switch over to this PhET simulation, then it'll show you that if you have the atoms separated, they're weakly attracted. So it's kind of slow. So we'll bring it in closer. We'll see it's just like gravity. It's going to pull it in, and then they're going to collide and bounce out, and this just continues. And so if we change to other atoms, go again, and we'll see that to oxygen, now that well is much deeper, so they come in, but there's a minimum there that's going to give us our bond distance, and then this profile here kind of explains all bonding. All right, so when they're separated, they're at certain energy levels, and when they come together and start to interact, then there's this minimization of energy that occurs, and so it's a favorable interaction. So if we'll pop back over, then we can see how we start to put all the information we had before. So we have Lewis dot structures we learned just looking at the valence electrons. And then this will explain the geometries that we see and the polarity and stuff like that. We can use it to estimate the enthalpy of a reaction. So it seems to work really well for it through average bond energies. However, when we try to mix this with what we learned in quantum mechanics, it doesn't really mix. And the reason is that if we look at carbon and we fill it in, we see we have two unpaired electrons. So this would indicate that it only wants to form two bonds with the orbitals from hydrogen with it. And so that's what we call unhybridized. And if we put those in, then we only get two bonds. And so what we find is that actually it wants to form four. So we explain this because it wants to mix. It wants to mix the S and the three Ps. And so we get this sp3. They both came from the two. So that's why we get this label here. And so it does this so that way it can form four bonds. And why is that better? Well, the valence bond theory shows that more bonds, the better, because we get this stabilization that occurs. And so it wants to maximize that effect. So versus if it only did it with the unhybridized, we would only form two bonds and we would see that bond angle. Everything would be 90, right? And so rather boring. And so now we can apply this to a little more complicated that you're going to get to and see how those orbitals are mixing and giving us the different bonds. And so everything has sigma bonds. Those are the initial bonds that we form and from those overlap. And so if we go to a little more complicated, then and we look at this structure, well, carbon has four bonds, right? But one is going to be pi and the other, oh, sorry. So it has sigma, all the initial ones are sigma, and then one is going to be the pi bond. That's what's given us then the second bond here, the double bond for it. And remember, this explains that geometry, that this is not tetrahedral, it's going to be trigonal planar and so on. And so we again can look at this complex orbital diagram for it, and we can see that we only have three things around it. So we would predict sp2. This leaves behind one pure p orbital, and that's what's interacting with the oxygen to form that pi bond. And so everything starts to gel together. We explain that second bond, that pi bond on it. And so now we can come in and we can look at, this is the worksheet I use to explain then the hybridization, is all you have to do, you can build up like this and look at it, but we can just count. And so we have AB3, so we have SP2, right? So three things are bound to that A, so we need three orbitals, one S and two P. And it get the same for a B2E because this lone pair of electrons has to be in an orbital. So it's the same. So that steric number now just describes the hybridization. If we go down to the next one, AB4, SP3, it ends up it's the same for all these because it all adds up to four things around that central atom. And now we get to the next ones. And we have a D because we have five things, but we don't have four p orbitals. So we need another orbital. What's the next one? D. So all these then have the same sp3d hybridization. And then the last one, sp3d2, explains everything that has a steric number of 6. So if you're going to determine the hybridization, you again have to do the Lewis dot structure, see how many lone pairs, because those need an orbital between it. One of the things that's confusing between is that double bond. And so if you started counting that double bond in here, everything would, all the carbon atoms would look sp3. All right. And the only reason why we get those different hybridization are those multiple bonds. So hopefully that will help you to kind of see the error ways as you start to do it. It's a common mistake and you have to just run through it. On the website, you have a bunch of problems that you can see it. All right.